Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 15, Vector Definitions and Operations. In this set of videos, you'll learn about some mathematical objects, vectors and matrices, which you need to render three-dimensional scenes. For the first few videos, we'll cover some of the theoretical background, and then in later videos, you'll use that knowledge to create a matrix class that will be fundamental in changing the position or orientation of the different objects that we'll be rendering. Matrices are also used to create a perspective effect, which makes objects appear smaller the further away they are from the virtual camera. But those will be covered in a later video. Right now, we're going to start with mathematical foundations. So in previous videos, you've learned how to work with vector data types in shaders. Vec3s, which are three components that are floating point numbers, and Vec4s, which have four components. For simplicity, in this video, we're going to talk about everything from a two-dimensional perspective, and in a later video, we'll explain how that can generalize to three or more dimensions. So to begin, we have the idea of a point. A point just refers to some location in space. It only makes sense if it's relative to some coordinate system, so we have to know where the origin is, and we have to know where the axes are. And each point is typically drawn as a dot. So for instance, here we have the point 2, 1, and over here we have the point 1, 5, and over here we have the point 4, 3. Okay? 3 points. In contrast, a vector refers to some type of displacement, that is, an amount of change in each coordinate. Technically, this can be drawn without reference to an origin, and each vector is drawn as an arrow pointing along the direction of displacement. For example, this is the vector 2, 3. The point at which it begins is called the initial point, or tail. The point at which it ends is called the terminal point, or the head. So this is the vector 2, 3, indicating a change of 2 units in the first component and then 3 units in the second. Here's the vector -3, -1, indicating a change of 3 components in the opposite direction, followed by a change of -1 in the other direction. Here's the vector 5, 0. This indicates a change of 5 units in the first component and no units in the second component. And here is the vector 2, 3 again. And again, it's 2 units and 3 units. Notice that you can have the same vector appearing in 2 different locations. You can calculate the distance between the initial and terminal points. That's called the length or the magnitude of a vector. And you can calculate that using the Pythagorean theorem or the distance formula, just based on these numbers. As we mentioned before, vectors aren't associated to any particular location in space. And so you can have the same vector appearing in 2 different locations with 2 different initial points. But if there is a coordinate system specified with an origin, if you draw a vector so its initial point is at the origin, that vector is said to be in standard position. Now, both these points, or both of these structures rather, points and vectors, they're both similar in that they're both represented by a list of numbers. However, they have very different geometric interpretations. Right, so to emphasize the difference between location and displacement, another analogy I like to use is the following. Consider navigating in a city where the roads are arranged like lines in a grid. If you were to ask someone to meet you at the intersection of 42nd Street and 5th Avenue, that refers to a particular location, and that corresponds to a point. However, if you were to ask someone in the city to travel 5 blocks north and 3 blocks east from their current position, that refers to a displacement, a change in position, and that would correspond to a vector. So again, even though they are represented with the same data structure, a list of numbers, they do have very different geometric interpretations. To make it easier to visually communicate with these, vectors are often represented with bold lowercase letters and enclosed with angle brackets. So for example, the vector 1, 4. Points will be represented with regular uppercase letters, so that is non-bold letters, and they'll be enclosed with parentheses. So for example, the point 3, 2. And in this context, to avoid any confusion, just a single number by itself is often called a scalar, and those will be represented with regular lowercase letters, such as x equals 5. And if we're using a lot of variables, we will often use subscripts to distinguish the different components of a vector, kind of so we don't run out of letters. So for example, I might represent the point P with components P1, P2, or the vector V with components V1 and V2. Now, one thing that we'll want to do is define some algebraic operations with combinations of vectors or points. And in theory, you can define any operation you want, but only some of them are going to make geometric sense. And so, we'll talk about a few of those right now. One of the most important operations is called vector addition. So given a vector u, u1, u2, and a vector v, v1, v2, vector addition is defined just by adding the components. So for instance, u plus v would be the vector with components u1 plus v1 and second component u2 plus v2. So for example, if you want to add the vectors 2, 5 and 4, negative 2, for the first component, 2 plus 4 is 6, and for the second component, 5 plus negative 2 is 3. Now, this also has a really nice geometric interpretation. It corresponds to displacement along the vector u, followed by displacement along the vector v. And the way you can visualize this graphically is you align the terminal point of u with the initial point of v, and then the resulting vector has the same initial point as u and the same terminal point as v. Right, so this is the vector w, which is the sum of u plus v. Now, in theory, it also makes sense to add a vector to a point with the same algebraic formula. Right, so you could think of this as translating a point P along a vector v to a new point Q. Right, so algebraically, you could say a point plus a vector gives you a new point. So for example, 2, 2 plus 1, 3 is 3, 5. As for 2 points, it doesn't necessarily make sense to add 2 points together. I mean, you could do it algebraically with a formula, but there's no geometric interpretation for adding 2 points. However, it does make sense geometrically to subtract 2 points. If you take this equation and you rearrange the components, you'll get v, vector v, equals q minus p. So you can think of subtracting 2 points as producing a vector that calculates the displacement between those 2 points. So for example, if you started off with the point 3, 5 and the point 2, 2, you could subtract 2, 2 from 3, 5 to get the displacement vector, 1, 3. And so those are some operations involving both points and vectors. There's another really important geometrically significant operation called scalar multiplication. Now, multiplying 2 vectors component by component isn't really useful geometrically. However, multiplying a vector by a constant does make a lot of sense. And this is called scalar multiplication. So it's defined as c times a vector v. Basically, you multiply each component, v1 and v2. Each one gets multiplied by that constant c. And this corresponds to either stretching or shrinking, or in other words, scaling the vector. The length of the vector is multiplied by the absolute value of c. And if c happens to be negative, the direction is reversed. So for example, if we start out with a vector 3, 2, if we were to multiply that by 2, we'd end up with a vector 6, 4, which points along the same direction but is twice as long. If we multiplied that vector by 0.5, we'd get the vector 1.5, 1, and that vector points in the same direction but is half as long. If we multiply that vector by -1, which I'll write as negative v, we get the vector -3, -2, which would lie along the same line but points in the opposite direction and has the same length. So that's another really important vector operation that we'll see a lot of. And finally, while we're talking about vector addition and scalar multiplication, there are two very special vectors called the basis vectors, which we're going to use a lot. Consider these two vectors. Let I be the vector 1, 0, and j be the vector 0, 1. Now, it turns out you can write any other vector. Let's say v has components x and y. You can write that in terms of these two special vectors, I and j, using the vector operations, vector addition and scalar multiplication. I should say vector addition. And it turns out you can do this in exactly one way. So what we can do is we can take the vector x, y. We can write that as x, 0 plus 0, y. So breaking it apart using vector addition. And then using scalar multiplication, we can factor an x out of this first vector. We can factor a y out of this second vector. And what we're left with is the vector I and the vector j. Now, any set of vectors with these properties is called a basis. Right? It's a set of vectors where you can write any other vector in your space as a combination of those vectors in exactly one way. There's lots of different bases for this space, but I and j are in some sense the simplest vectors to work with, so they're called the standard basis for two-dimensional space. And these vectors will become really useful for us when we're talking about special kinds of vector functions and when we're thinking about different geometric transformations later on. But in terms of vector algebra, that's all we need to know for now. And in the next video, we'll start talking about some special functions that transform vectors into other kinds of vectors called linear transformations. So we'll see that in the next video.